Welcome to the last week of the class. Today, I'm gonna go over some practical considerations, sort of wrapping up what the finite element method is used for, and some tips about element selection. I guess the way we started the class was by saying that the finite element method is a way to solve PDEs, but then we really only focused on heat transfer, a very simple problem in 1D and 2D, and also linear elasticity. So that's as much as we did in class, so that you had an idea of how to go from the strong form to the weak form, how to introduce the discretization using the shape functions, how the combination of these two leads to the stiffness matrix and the force vectors, and then you have your system of equations that you can split and solve. So that was sort of the map that we followed all along, but for these very simple PDEs. And what I want to say, first of all, in this lecture is I want to talk about what are other problems that you can use finite element method for that are beyond heat transfer and linear elasticity. So as I said at the beginning of the class, most physics can be represented with PDEs. Usually you will get them in the strong form, so the classical form of the boundary value problem. And then the FE methodology allows you to turn it into the weak form and in order to get the system of equations and solve it. In this class, we have focused on nice PDEs, meaning the operator is linear. So by the operator, I mean the derivatives. It is elliptic. It is self-adjoint. So it has only a second order derivative, no first order derivative terms. So if you recall the heat transfer equation, it just has like this second order derivative for the temperature. The linear elasticity only has the second order derivative for the displacements. It's self-adjoint, so meaning it's a symmetric operator, and it only deals with a single field. So either in the case of the heat transfer problem, only temperatures. In the case of the linear elasticity problem, only displacements, but no extra combination of fields, no constraints. One of the examples of a constraint would be incompressibility, where you have to satisfy more than one thing. You have to satisfy the linear momentum balance with the displacement, but you also have to satisfy incompressibility. So that means that you need some extra field that you need to solve for, and that's the pressure to prevent compressibility, for example. Um, so we restrict our attention to this linear operator, elliptic, self-adjoint, single field. And in this case, if you apply the finite element method, then you get a linear system of equations, which is symmetric and is very well behaved. So it will converge to the correct solution, provided that you have shape functions that are complete and continuous, and provided that your geometry doesn't have any singularities, any kinks, for example, or 90-degree corners. So that's good. Obviously, it depends on the mesh refinement. But if you refine your mesh enough and you don't have these features of the geometry like 90-degree corners, then your solution should approach the analytical solution. And as I said, the best examples of this very well-behaved problem are heat transfer and linear elasticity. However, there are many other types of partial differential equations for which the finite element method can be used. For example, other problems in solid mechanics, when you have linear but incompressible elasticity, then if you just use a blind finite element approach, then you get an ill-conditioned system of equations. The system is over-constrained because you need to satisfy now both the linear momentum balance and the incompressibility constraint. So this leads to something called volumetric locking that we talked about last lecture. And then you converge. If you refine the mesh, you converge to a solution. The problem is that the solution is wrong. So how do you deal with this? Then you need to have a multi-field formulation where you introduce an extra variable, a pressure field. And then in Abacus, there's something called hybrid elements, which have this additional pressure field. But we didn't talk about that. So that's just something for you to keep in mind. We deal with simple problems, but if you need to solve other types of problems, I just want to give you an idea of what are the other problems that you can solve probably you need to go and look up a little bit more information, but you could, um, you at least will know about them. So this linear but incompressible elasticity is one of them, and then that one is addressed with hybrid elements. This is an example of oscillations in the pressure field. So when you have the pressure and you don't take care of choosing the correct elements, you might get instabilities. So again, I guess I just wanted to have this visual uh, to show these are different formulations that lead to, smooth pressure fields. But this one clearly, for example, is it's not, it doesn't look right, right? And this type of pattern that you see here, that's an instability. You have these high and low regions of pressure. So when you see something like that for this type of problem, or for other problems in general, when you're solving for something and you get this type of oscillations, then you should think that there's something going wrong. So you have um, to be looking for this type of patterns. Other problems in solid mechanics that we didn't talk about: nonlinear elastic materials are and nonlinear geometry. The basic concept is the same, actually. The strong form is the same, and the weak form is the same. Even the element basis functions are the same. But for example, if you are considering non-elastic materials, then the stress is a nonlinear function of the strains. In what we have done for the linear elasticity problem, we have the stress equals this D matrix times the strain. So it's a linear relationship between the stresses and the strains. But in some materials, there's not a nonlinear relationship between the stresses and the strains. So that would make that even if you have the same weak form, now it's a nonlinear function of the strains, so you cannot solve it just the way we did. So that's one. And the other aspect when things change is when you have finite deformations. Remember when I was saying what were the constraints on the linear elasticity problem? What we said was that the deformations have to be small, such that you stay within the elastic region, the linear elastic region of the materials. But in some cases, like rubbers or soft tissues, then the formations are quite large, 20% strain, for example. So in that case, even though the strong form is the same, now you need to account for these changes in geometry. Because then remember when you are doing the integral, um, that one you need to account for the changes in geometry. The strain calculation, also we have been using the linear version of the strain, but there's a non-linear version of the strain, so you also need to account for that. And these are things that Abacus can do, and then you just need to learn a little bit more about nonlinear elasticity. In a few things is you have to basically define the material different from what we have used now. So you have to choose, for example, hyperelastic material, and we won't talk about that. Um, but that's something that you need to learn on top of what we have talked about in class. What was the other thing is the nonlinear geometry. That's actually very easy. You just need to click an option for the nonlinear geometry. I think probably the nonlinear material is it's just a little bit more hidden in Abacus. There are also issues with incompressible behavior, and then you also need to use the hybrid elements. Um, and now, because you have a nonlinear system of equations, then you cannot just solve with one, inversion of the stiffness matrix. You actually have to do iterations. So hopefully you have done a little bit of Newton-Raphson to find the roots of a polynomial. And so in that process, you start with a guess for where the roots of a polynomial are, and then you try to, well, you evaluate your polynomial and the derivative, and based on that, you get a new guess, and you continue like that, and eventually you converge to a solution. Also used for solving in general some nonlinear equation. So not just for polynomials, but in general to find a solution of a nonlinear system of equations. So this is what Abacus does. It has an initial guess for the displacements. Based on that, it evaluates how close it is to equilibrium and the derivative of that. And then with that information, it updates the solution, evaluates again how close it is to equilibrium and the derivative of that, and then updates again the displacements and so on until it finds the displacement that actually produces equilibrium. But now the fact that you have to do these iterations means that you have the risk of not finding the solution. So you have, instead of convergence, you have divergence. For example, if your solution starts growing and then explodes because of some underlying reason, for example, you are not very close to the solution, so you start exploring a space that is farther and farther from your solution. So you have to be very careful with how do you apply the load, and you have to do apply the load incrementally to try to get all the configurations of the material uh, slowly, gradually. There's some issues when you are doing, large deformations, nonlinear materials, is that there are instabilities. Again, you have patterns of the deformation that are, I guess, not nice, smooth, and incremental. Uh, Probably you've heard about, I think you did this in the 323 class, Euler buckling. So buckling is one type of deformation that can occur where you are applying a load and then there's a region or a level of force at which there is deformation without extra force, and actually the force goes down. So it's easier for the material to uh, deform even while you're not applying any load. So in that case, if you are trying to control the load and increment the load that you're applying to your part on Abacus, then you won't find the solution because for that buckling, the load will actually go down. And I have a slide later on showing that. So you have to be careful with that. There's some special techniques in Abacus. There's something called buckling analysis that you probably have to do if you have a structure that has this type of instability. Then there's also nonlinear inelasticity. So nonlinear elasticity meaning the same as the linear elastic case, but with nonlinear functions either for the strain or for the stress. But you can also have inelasticity, meaning plastic deformation, viscoelastic deformation, damage, and then for biological tissues you can have growth and remodeling. So Abacus can also do this, but again, you need more information about plasticity or damage to make sure that your implementation makes sense. So again, what we have done in the class will be good enough to find the stresses, but without any plastic deformation. So you want, right now we are not in a place in the class where we can say, the material is yielding in this part of the simulation and it will deform permanently. So we have not done any of that. We have only dealt with the linear and elastic part of the deformation. But Abacus can do the part where the part deforms permanently. So plasticity basically. The strong form and the weak form is the same, but the thing is that now the stresses are not just related to the strains, but they are related to the history of the formation. So you have to keep track of some internal variables to keep track of how the part has deformed permanently. Again, not something that we have done, but something that you can definitely do with Abacus. This is just one example of nonlinear deformation and nonlinear material. As I said, one of the examples is for soft tissues. So you can see this is something that we do in my research group. So we try to get different ideas for reconstructive surgery and which lead to very different stress profiles. So in this case, you can see that the strains are definitely above 1%, more on the order of 10 to 20%. So then you definitely need the nonlinear geometry. And I don't have the material properties, but it's nonlinear. It looks like an exponential curve almost for the stress strain response. So again, you can do this with Abacus. These simulations were done with Abacus. But you need to learn a little bit more about how to enable this nonlinear material nonlinear deformation. Other problems in solid mechanics. I thought I had the buckling slide. Maybe I'll have it a little bit later. So just keep that in mind. Other problems in solid mechanics: beams, plates, and shells. In this case, the strong form is different. So you have a higher order derivative. You probably did this for 323. You did beams for 323. So you have this fourth derivative. So that's different from just the second order derivative that we have for the linear elasticity problem. So because of that, actually standard elements are not enough. You need to have different shape functions, for example, and yeah, it's just another field. I think there's one um, chapter at the end of the book. I think chapter 9 that talks a little bit about beam elements. So maybe if you're curious, take a look. I'm just gonna give you a very very brief rundown on this. Yeah, I just want you to know that there is a way to model elements that are not solid elements. Um, and this is different from, I know we have done the 2D linear elasticity, but in that case we are still considering, solid elements, but just in 2D with either the plane strain or the plane stress condition. But these beams, plates, and shells elements are, for example, for the beams and shells, you have 1D elements or 2D elements, but embedded in a 3D geometry. You in principle you can resolve structures with solid elements even if they are very thin, but the problem is that you need, and we did this for the beam, the cantilever beam example. If you are trying to solve a cantilever beam with the standard elements, you need to have several elements across the thickness, or otherwise you get really bad results. And as opposed to using beam elements, which basically you condense all the information of the thickness into just a single element. But that's why they require higher order derivatives. So they are definitely computationally, in terms of computational power needed, it's much better to have beams and shells and plates as opposed to trying to discretize everything with the solid elements. But as I said, because they condense all the thickness information into one equation, then the strong form is actually different because it has to account um, for this thickness deformation. Again, Abacus can do this. It has shells and beams for linear and nonlinear materials. We won't cover it in class, but this is something you should keep in mind. Another problem in solid mechanics that we didn't talk about, but that you can solve with the finite element method, is dynamic problems. So in this case, the strong form looks a little bit like the one that we have done, but it has the addition, so divergence of the sigma plus the body force equals rho times acceleration. So it has the acceleration. So this is no longer an elliptic problem. The solutions are not necessarily smooth. There can be oscillations, waves, buckling, and then the solution, because now you have this acceleration, you actually have the acceleration, velocity, and displacements. And to get the solution, you need to do integration over time, similar to what you did for the transient heat problem. There are several options to do this, basically two, either explicit or implicit methods. This is needed for impact, for example. Again, we won't talk about this, but Abacus can do this as well. So again, you just need to maybe look for a little bit more information before you do this, but just to keep it in mind. This is just one screenshot from the Abacus documentation. One of the things that I want you to do after you leave this class is, yes, you know the basics for the finite element method, um, and then we haven't covered all this. I'm just gonna give you sort of a list of all the things that you can do with Abacus that we are not doing. And then, because I'm not giving you all the details, one of the things that I want you to remember is that there is, for example, an Abacus user manual. And that one has a lot of information about the different elements. It has some examples, it has some tips. So one of the things that I would like you to do is, if in the future you have a problem that is not one of the simple, linear elastic material, that you need to use a shell element, for example, just you need to do a lot of reading on your own as well. Getting obviously some expert opinion, studying, maybe taking more classes. But if you learn on your own and also look up the documentation, the Abacus documentation, for example, you'll get some idea of what the different elements do, what the notation is, and then there's going to be examples. So just keep that in mind. The Abacus user manual is pretty useful. This is just one example of how shells can be used to optimize roofs. So you can see that the structures here are very, very thin. So this is essentially like a surface in 3D. So for these type of problems, yes, you could use solid elements, but you will need a ton of elements because you need to capture the thickness direction. Instead, what you can do is you can use shell elements where they are basically, a surface. So then you save a lot of degrees of freedom. But the problem with that is that, yeah, it needs a little bit of a special formulation. Hopefully this is one of the last ones that I have. Other problems in solid mechanics that you can use, solve with finite element analysis, eigenvalue analysis. So for example, for the elastodynamics equation, you can pose an eigenvalue analysis to determine the vibration modes of a structure, or you can find the buckling or other instabilities. So Abacus can do this. We won't demonstrate it in class, but there is a eigenvalue analysis in Abacus. And again, as I say, it's used to find vibration modes or buckling or other instabilities. Fracture. Again, I think, I don't know if someone asked me about fracture. That's also something that you can do with Abacus that we have not done. So again, we have restricted our attention to the part of the deformation that is linear elastic. But if you are interested about the crack propagation, then again, one of the things, maybe take some class on fracture mechanics. Here you need to have different types of elements. Abacus can do this with either something called XFEM or cohesive zone elements. So that's something that I use in my research. So again, just keep in mind that Abacus can do it. You probably need a little bit more information. Fluid mechanics, advection and transport, for example, Navier-Stokes. I don't think it's as commonly used in Abacus, and actually the finite element method may not be the first option. And this is because usually you have a constant volume, so you can use other types of discretization, such as finite volumes or finite difference. So the finite element method is not really always used for Navier-Stokes, but it can be used. And CFD is a field of its own. I think we have a class at Purdue for CFD. So yeah, Abacus can do some, but I would say for CFD, Abacus is not the top choice. So again, get more information, and then probably different software for CFD. Yeah, this is, I should have had this one up above, but this is what I was talking about when I was saying that there's instabilities where you can have you won't converge the solution. So this is the classical snap through instability. So you're applying a load on a beam, and then at some point the beam will basically flip over to the other side. And then when that happens, you're applying your load, and then at some point, actually, while this thing buckles, the load required to have the deformation, so this is the deflection of the curve and this is the load. So here the load decreases as this thing deforms. So that's negative stiffness part of the curve, right? And then that's because in this process right here, then it's easier for the beam to deform without extra load. So actually you have to, your load will go down as this thing happens, and then it will slowly go back up again once this thing is flipped. So once it has gone through this snap through instability. So that's the type of problem that it won't work in Abacus if you don't take care of this point that at which you have this negative stiffness. So that's why you would need to do some buckling analysis in Abacus, because you're If you just use Abacus blindly, you will be able to get to the cusp of this load curve, and then but that's it. So you will be able to find solution up to this point, and then it won't work for this point unless you do a little bit of this buckling analysis. And I think this is the last slide. So this is another type of instabilities that you can solve for if you're interested in wrinkling patterns. That's something that you can use Abacus for. And I'm gonna stop right here, and I'm gonna have part 2 of the video for some tips on how to select elements.